Okay, so this is a talk for the students, essentially, and I assume that you have never heard anything about artificial neural network, but you might have heard that something is happening, and you might have learned here the word deep learning or this kind of stuff. So I would like to give an introduction about these kind of systems, and then at the end of the talk I will mention some open problems and some solutions to these open problems. And there will be a big jump. So we'll go from a very introductory description to a very, say, sophisticated question at the end, but I hope that you will find it of interest. So essentially, I would like to dissect what deep networks are and what how deep learning works. This is a very heuristic field of machine learning, but it's kind of effective. And then I would like to ask once I've described this to you, I would like to ask the question, how it's really possible to do learning with such huge system without essentially overfitting the data or this kind of question. And then I would like to say what I think is going to happen in the future. So just an historical remark. There's been a lot of interest in neural systems, say in the 80s and in the 90s, but somehow in modeling neural systems. But somehow the interest disappeared a bit around the 90s for many reasons. One reason was that the computational performance of the artificial neural systems were not particularly satisfactory at that time. Maybe the data were not good enough, and certainly the biological data were not sufficient to motivate modeling and so on and so forth. So there were many reasons. However, something happened around 2005. Let me say, this is a kind of an arbitrary date, and just to simplify things very, very much, is around 2005, people started to use GPUs. You know what the young people know what the GPU is, right? It's the graphic processing unit of your laptop. And so programmers started to use the GPU, which are more powerful for certain operations than CPUs. And so all of a sudden, they were able to do huge computation on a huge data set. So again, in the same period, also a lot of data became available. So all of a sudden, what happened around this period is that these kind of tools that somehow have been discarded in the 90s started to have fantastic performance. I mean, on all the benchmarks to which they were applied, they started to beat all the other traditional methods. Okay, this is more or less. And at the same time, the biotechnologies, say the technologies for measuring what's going on in the brain have also improved a lot. Okay, so let's dissect a deep network. So what is this deep network? So imagine a system like this, but I mean, this is just a sketch. So imagine this multiplied by 1 million, okay, times. So a deep network, you should think to a deep network very roughly as composed of two parts. A first part of the network, which is devoted to the feature extraction from the data. So if you have an image, for instance, you want the first layers of this network somehow extract what are now called the features of your images. And I will try to explain what this means. So a lot of layers are devoted to this. And then there's a second part of the network which associates the features to some classified labels for the data. So somehow you give an image here, you decompose it in relevant features, and then you learn on this side of the network to associate the image to a certain classification. Okay, so somehow this part is feature extraction, this part is supervised learning. Okay? And one thing that one should keep in mind is that you can have millions. So the parameters in this system, okay, what is this system? I mean, each node here is a so-called neuron. It's a formal neuron. It's just a nonlinear device that takes the sum of all incoming signals and performs a certain nonlinear operation. Okay, so each circle here takes all the inputs from the previous layer, and each input is weighted by some matrix W, some coefficients, okay, and outputs a signal which is a nonlinear function of the input that he receives. Is it clear? It's a very simple object. Okay, this is called the perceptron, the neuron, formal neuron. Okay, how many W's can you have in such networks? You can have 100 million, for instance. There are networks that have such a number of parameters. So it's a kind of a huge object, which is not too far from certain real circuits. So somehow a more reasonable picture of a deep network is this one. So you have a first set of blocks which are devoted to feature extraction, and then another set of blocks which are devoted to supervised learning. But you have to imagine that each block in turn is a tremendously complicated object with an enormous number of parameters. That's the object, okay? And your goal will be to find the weights on these links such that overall the system performs what you want. And in particular learns from examples and generalizes to things that he has not seen yet. So what are features? Very roughly, I mean, a feature in this picture could be, the fact that you have a vertical line here, that you have, a white spot here. I mean, there are many types of different features, low-level, high-level features, and so on and so forth. And you shouldn't forget that the machine only sees numbers. It doesn't see all the, but okay. So let's discuss a bit what it means to extract features. I don't have time to go into algorithms, but just roughly. So now it is the same network just turned up. And so the idea is essentially that, say, the first layer somehow is able to identify the most elementary geometrical features. How do you detect that? Well, you just activate one of these neurons, and you project back in the input what is the image that, and you observe the image which is projected back by that neuron, okay? And so, for instance, you can find out that this neuron is going to project back an image that has a lot of vertical stripes, and so on and so forth. So, in this way, you are able to understand and interpret the fact that the first layer is extracting features that are very elementary. The second layer is extracting features that are a bit more complex. And again, how do you detect that? Well, you propagate back the signal and see what you find in input. Okay? So you can imagine that a picture, you input a picture here, and then you decompose it into lines, and then into noses or eyes, and so on and so forth. And at the end, you have a high-level feature, and then after you have extracted the high-level features, the network has only to learn how to put together this feature in order to learn the association. Okay? So this is what's happening. The most commonly used network for images is, for this pre-processing phase is called the convolutional network, so convolutional layers. And essentially, I don't want to enter into the details, but essentially what the convolutional layers do is that by some sliding windows, they are able to implement translational invariance. So if you have, say, a nose here in this angle or a nose there, it doesn't make any difference for the network. So it cures this kind of geometrical problems you would have in analyzing an image. So you can imagine that this is a picture, and so you have a unit here that identifies the fact that there's a pupil in the picture, another that identifies that there is an eye and a nose, and then you go to the next level, and you will have a unit that recognizes the fact that you have the things together, okay? I'm being very, very rough here, but I want to give you the principle, okay? And this network can be huge, really huge. If the input is not an image, but is, like some molecular biology data set or whatever, you use other techniques to extract features, and one is the restricted to a machine. Essentially, you have an input layer here, and you have essentially, you want to compress information without losing information. And so somehow you learn the weights here, you find the weights here such that once you trace out, you sum over all configuration of the hidden layer, you reconstruct the probability distribution of the input. Okay, let's say that I don't want to enter in the details. Let me, if you're interested, we can talk later, but the key point is that if the images are not, so the inputs are not images, you have other technique to compress information and extract features, okay? One is our restricted Boltzmann machine, another is called autoencoder, and so on and so forth. So there are many techniques. Okay, so at the end, what a deep network does is that you give an image in input, it extracts a lot of features, then it projects the feature into the learning part of the network, and then at the end of the day, it's able to tell you that the image was the image of Sarah. Okay, and this for, okay, real deep networks, this is again a cartoon, a real deep network look like this, more or less. So you give an image, which can be a very complex image, And it's able to perform a segmentation, identify where objects are inside the image, and then for each piece of the image, it's able to implement that kind of process. So somehow, we will see later, the network is able to actually tell you what's in the overall picture, which is kind of amazing. So, somehow, for instance, suppose that you give this input. Sorry, I don't know, there's another input there, but let's say, suppose you give this picture as an input to the network. This will activate the neuron inside the network. And then suppose that somehow you tweak a bit this neuron, you try to activate them a little bit more to see which are the most relevant features. And somehow you understand that what the network is trying to do when looking at this image is somehow it sees the image this way. If you try to amplify the features, you see that, in fact, the way the network sees the image is more or less this. You see that here there are a lot of geometrical features, okay? So this is somehow the way the network sees really what's going on in this image, given the architecture. It's pretty nice. Now, so let's consider now an application, a totally useless application of this. So suppose you have one of these networks, and let's focus just on the first part. The first part is the feature extraction part. I don't want to consider for the moment the learning part, okay? And suppose you give an input, an image, and then at a certain layer, you have to study the problem, but I mean, believe me now, at a certain level, you will have blocks that characterize geometrical features, the fact that in the image you have angles, circles, straight lines, or whatever, okay? And also, you have a feature that I call style feature that are more related to the texture of the image, okay? So the fine, the colors you use, the contrast between different colors. I mean, let me call style feature, okay? This is a work done by a group in Sweden. I don't have time to tell you exactly how it works, but you can imagine that this is possible. So what you can do is, well, you first of all input a Van Gogh picture to this network, and you actually try to memorize which are the style features of this Van Gogh picture, okay? Then the next thing you do is you give as an input a picture that you have taken with your camera, and what you will observe certain geometrical features and some different style feature, right? But then what you can try to do is to, by some algorithm, it could be a Markov chain or whatever, you start to modify your input image in such a way that you want to preserve the geometrical feature, so you don't want to change the fact that there are houses, there's a river, and so on. You want to preserve all the geometric information. But you change the pixel of your image in such a way to reproduce here the Van Gogh style features, okay? And this is what comes out. It's pretty amazing. So this is when you try to reconstruct Kandinsky's feature given this image. This I let you guess. This is Munch, okay? This is how the network produces this, transforms this feature into a Munch picture. And this is the Van Gogh version of this picture. And I let you guess who is this one? Picasso, okay? Now, this gives you, it's useless, I mean, it's fun, right? I want to plug in some pictures here, but it gives you an idea of, it's kind of amazing, right, to see this. I mean, I was really surprised to see how it works. I mean, I'm sure it can be obtained in many other ways, but this is real work. So let me give you another example of how this network works. And in particular, here, you would read here how this is another deep network that is going to translate a speech into a written sentence, okay? So let me see if I can let you hear. Okay, let's see. Oh, sorry, I made a mistake. I don't know what I should do here. Probably this.
This reality begins to explain the dark power and otherworldly fascination of 20,000 Leagues Under the Seas. Nemo builds a fabulous futuristic submarine, the Nautilus, that conducts an underwater campaign of vengeance against his imperialist oppressor. His specifications for an open sea submarine and a self-containing diving suit.
Okay, sorry, I stopped it. There was a mistake. You notice that at a certain point it made a little mistake, but still it's kind of amazing to see how it works. And there are many other applications of this type. I don't really have time. Oops, don't really have time. I mean, this is an example of a deep translator, which is again amazing. Translates here is from English to French. The reason is that Facebook has a research lab in Paris, I think. And you see that it can translate by keeping track of the relationship by words and not just by looking at the letters. So it's really kind of an amazing thing. And let me conclude, as far as the application is concerned, with this kind of observation. So what this network can do is take a picture, try to do they are able to classify what's in the picture by identifying, the portion of the picture in which there is something. Then by doing segmentation, they're able to identify what these things are. So for instance, if you provide to the network this kind of image, okay, this is what the network is going to tell you. Okay, road, here is a car, here there's a window, there's some sand. Well, it's not really sand, but okay. And so on and so forth. Now imagine that you're blind, and when you are blind and you connect to the computer, you have an audio system that tells you what's on the web page, and most of the information is visual information, and for each image nowadays you get nothing. You get just no sound at all. Here you start to have all the information about the content of the picture. So it's kind of interesting, right? So there are many applications of learning in general and deep network. And let me stress that deep learning is just one component of all these machine learning tools. Okay, I'm just talking about this but there are a lot of. So we have seen something about object recognition, speech recognition, but then there are a lot of other applications in economics in particular. There are also people starting to work seriously on these topics, and I don't want to talk about this on purpose. Now, so I don't know how much time I have, but if this is clear, now I'm going to ask a real question. No, wait a moment. There's another thing I want to, before I continue, there's another topic which I find amazing of this kind of object, that is, can they behave in a kind of an intuitive way? Okay? Well, in order to answer this question, people have somehow tried to use these systems to play games. Okay? To play games, and the kind of learning technique you use is called reinforcement learning, which is a little bit different from the kind of learning algorithm you would use to segment images. It's a bit different, but I don't have time to enter into the details. But look at what happens. I find it really amazing. So I'm sure even though you're very young, you have seen this game. I gave this lecture to the academy in Che, where everybody was somehow beyond 80, so I had to use it. But anyhow, I'm sure you have seen this game, okay? So let's see, okay. So here you want to learn how to, okay, you know this game, right? And you see at the beginning, the network only sees this number, and it has to decide how to move this brick. And so after 200 episodes, it starts to play a little bit. That number. Oh, sorry, I made a big mistake now. You shouldn't ask questions.
It's learning the payoff, not the strategy.
Okay. So I don't know how to stop this actually, but the input are the pixels of the image, and the scope of the network is to maximize this payoff. Okay? And at the beginning, it doesn't even know how to make the ball bounce back. So at the beginning, it's very bad. After 300 episodes, it starts to be smart. And the input is really very elementary. Starts to be smart. You see, very good. But at a certain point, it starts to be really great, because look what happens. This was published in Nature 2 years ago, so it's not. So after a while, the network learns that it's kind of convenient to throw the ball behind. After this happens once, again, you see it goes again back. It understood immediately that was a very convenient thing to do. And actually, you will see that it's going to also learn that it can be done also on the other side. So it's really amazing how this can be done. So you know better than me that there's a long tradition of algorithms playing games, right? And you know that in '97 there was, Deep Blue was able to beat, I don't remember, Kasparov was the name of the champion. Anyhow, was able to beat the best human player in chess, essentially by a smart way of exploring the whole decision tree of the game. So chess has about a branching ratio of this tree of about 20, and so somehow it's possible by searching the tree in a smart way to actually predict the outcome of a game. Okay? And so what this computer was able to do is to beat a human by brute force, essentially. Now, I don't know how, but I know there is an app for your phone which can beat any human. And the difference with the algorithm at that time is that your app is very efficient in pruning this tree, in avoiding the exploration of a lot of parts of the tree in which you can predict easily that would not contain any useful strategy. Okay? But last year, what happened is that, but still there was a game, which is called the game of Go, that was considered to be out of reach. The game of Go is very simple. I've never played Go, but it's very simple. You have stones. You have black and white stones. You have a 19 by 19 grid. And once you put stones, you cannot move them. Okay? So it's not a very dynamic game. But a black stone can be captured by white stone if it is surrounded by white stones. Okay? And the final objective of this game, you see, it's very elementary. You have two types of stones, a blackboard. It's full information, no luck at all. And the final objective is to control at least 50% of your grid. What this means is complicated. I think most of the time in this game is spent in deciding whether you have actually controlling or not 50%. But anyhow, this is the game. Okay. Now, what is the branching ratio of this game? It's about 300. It means that you have 10 to the 72 possible configuration of the game. So there's no way you can explore this search tree. No way. Okay? So I will be very fast, but what people did recently in this, the AlphaGo group of DeepMind, it's a company that now belongs to Google, they essentially trained several networks to play this game. First of all, they pre-process the information by this convolutional network because this is a geometrical game, so you do have invariances that you want to implement. But then essentially, they use network to evaluate in an incomplete way the validity, say, of a strategy. Okay? You cannot explore the tree, but somehow by playing against other networks along the game, they are able to give a score to the various possible moves. Now, this is a game in which you have so these are networks that use both some logical rules that come from the experience from the game itself, from the history of the game itself, but there's a huge component that is provided by learning. And in this game, you have the World Championship, and then you have the European Championship, and then you have normal players. I don't know, some of you play Go? No, nobody. Anyhow, so the European Championship is in the world ranking is number 650. Just to say that there's a gap between Europe and China, Korea, I don't know exactly. Okay, so what happens that the AlphaGo group decided to play this game against the European Championship, and this is what happened. And so this was about 1 year ago. So the European Championship lost 5-0. Okay, and then a few months later, they agreed to play with Lee Sedol, who was this famous world championship, unbeaten, and so on and so forth. And this is what happened again. And I mean, it lost 4-1. It won one of the games, but nowadays it would lose all the games because this machine learn, and so there's no. And what is interesting about this is that it's not a deterministic game. There's a kind of intuition going on here, and so this will really consider as a benchmark for AI. Okay, so I think it's interesting. Yeah, but I mean, it's the evaluation. No, the point is that you cannot explore the whole tree. So you.
No, I understand. Show me, I can
we have dinner together, okay? But I mean, okay, what I just want to say, that's for the sake of this talk, is just that, you have very incomplete information. You have this network that, somehow give a score to their strategy by playing with other networks. Like we play with other humans, they play with other networks. That's more or less the idea. Okay, so now I don't know how much time I have because, okay. So there are a lot of, kind of, say, challenges in machine learning. People are thinking about what is called differentiable computing. Essentially, somehow they would like to have a computer that is programmed like you train this kind of network. So this is and then, but essentially the bottleneck for this network is really the unsupervised learning part, because most of the data that are available do not have labels. You have an image and you don't know what actually this image is, right? So for instance, there is the Connectome project, you might have heard of this. They take a cubic millimeter of the brain of a mouse, okay? And they start to take a picture of the top of this cube and they put it aside. That's one picture. Then peel away the surface and the thickness is less than 30 nanometers, okay? And they take another pictures, and so on and so forth. At the end, you have 10 to the 15 voxels of these images, and they want to put them together to reconstruct the three-dimensional wiring of the brain, which would be very interesting, right? The problem is that you don't know how to reconstruct things because you don't know how to label the objects. So now they're using these kind of tools to reconstruct things, but the way they started with is by hiring a lot of students and asking them to label the pictures. But, you can do it for 1,000, 10,000, 1 million pictures, but not for 10 to the 15, right? So it's really, so unsupervised, how to extract features that are not classified is really the big challenge for the futures. And let me say that we are still completely far away from any form of artificial intelligence in the general sense, okay? So building really causal models and so on. So these are just statistical inference machines, essentially. But somehow the perception of what you can do by this is really impressive. Not only by this method, also by that method. So maybe we have to rethink about, what is relevant and what is not relevant. So the question I would like to address in the last 10 minutes or so is how can learning take place in these systems? So you have a system with 10 to the 8 variables, which is this very complicated network that performs a nonlinear transformation of the input to the output. And you want to, typically what your objective is to find the W's, so the weights that connect the different nodes in the network, such that the error that the network makes on a given training set is minimized, right? That's you want to minimize a highly nonlinear function in a huge dimensional space. And so the algorithm, what they try to do, there are many, many different algorithms, but essentially they are variants of what you would call of a gradient. They have this high dimensional problem, and algorithms are variants of gradient backpropagation. Now, one should say that learning algorithms have evolved in the last 30 years or so, or even more, in a very, according to a sort of an evolutionary scheme. So there's no principled really way of, the algorithms that work have been designed by practitioners that have somehow compared performance and so on. So at the end of the day, now people use algorithms that are not derived in a very principled way, okay? So for instance, you will hear the word stochastic gradient, dropout, all these kind of algorithms are actually not really, for instance, they're not performing a gradient to start with, okay? So there is a huge lack of understanding of when and why these algorithms work, okay? And so I will try to at least give a partial answer to this question. So as I was mentioning, you have to imagine the learning problem for this artificial system as a problem of minimizing the number of errors. Since I'm a physicist, I call this number of errors an energy. You would call it a cost function, and there's no difference, okay? And so essentially, this function, which is a function of all the parameters of your system, counts the number of errors that the network makes. Forget about the formal expression, it's not very important, okay? So this is just the number of errors on the training set. And it's a function in 10 to the 8th dimension, highly nonlinear. So what you would expect here is to have certainly a lot of saddle points, local minima, whatever, right? Unless the input you give are totally correlated and totally trivial. Okay, if you give to the network always the same input, it's very easy for, you would probably have just, kind of a very smooth landscape. But as soon as you give non-trivial information, non-trivial inputs, and you make association with non-trivial outputs, then the circuit becomes, in principle, very complicated. Okay, so, and the interesting observation, at least to me, is that if you look what the effective algorithm do, is that they try to somehow minimize the energy, but they never quite do that. So you have no real algorithm that works, which is actually trying to minimize this energy. And so this is a kind of a paradox. So the idea is that if you just do a gradient, you get stuck in a local minima, and that would not work. Okay? So for instance, what they do is they do a stochastic gradient. I mean, machine learning people do stochastic gradient, in which they take just a few examples, they compute a partial gradient, and then they move. But when you compute a partial gradient, you're doing something wrong, so you're adding noise to the system, and therefore you are not actually minimizing that function. So it's really not, they're always doing something different. Okay? I should go through all the algorithms, but this is more or less the scenario. So how do we understand this? Okay, in order to understand this, let me go back to the simplest, just to one single neuron. Okay, let's consider, instead of 10 to the 8, it's sufficient to consider one neuron, and we will understand what's going on here. So we consider a neuron, so just one node. Imagine that you present an input to this neuron. The input is multiplied by the weights, and this gives you the total signal that the neuron sees, and the neuron performs a nonlinear transformation. Okay? And let's assume that everything is binary. So the input is binary, the weights are binary, and the output is binary. And what you want to do is to learn a set of association input-output. You want to associate a random vector, for instance, to a random output for a certain number of times p. Okay, this is your problem. You want to learn random patterns with this object here. And so you can define your energy function, which is the number of errors that the network is making, which can be written in this form. So you count 1 whenever the sign of the output is different from the desired output. Okay? And you add 1. So this is just the number of errors that the network is making. And you can ask yourself, okay, how is the shape? Is it possible, first of all, to learn random patterns? Second, how does the geometry of this space look like? Do we have local minima? Do we have, what is the scenario? What's going on here? Okay, so, this model was solved exactly by Werner Kraut and Marc Mézard in '89, and they were able to compute the maximum capacity of this single object, which is called the binary persectron. For those of you who know something about computer science, keep in mind that learning with binary weights is an NP-complete problem in the worst case. So it's not, even though it's just a neuron, it's not a totally trivial object. Anyhow, if you now ask yourself, how does the geometry of the space of solution, in the space of the W's, so take all the set of W's such that all the patterns are correctly classified, okay? So the space of zero energy. How is this space? How does it look like? What is the geometry of the space of solution? Is it clear what I mean with this? Okay, it looks like this. So all solutions are very far one from the other. So somehow the space of solution is scattered around, I mean, this is just a pictorial. It's an hypercube, of course, because I said I considered binary weights, so it's an hypercube. And somehow all solutions are far away one from another. Okay, this is the prediction that comes from the theory which looks at the dominant contributions. Okay, the vast majority of solutions are of this form. So they're just points. Okay, so essentially, if you think in terms of local minima, these are very narrow local minima. Okay, so somehow the scenario you should have in mind is that you have a lot of local minima at non-zero cost, and then you have some optimal solution here and there, but these are far away one from the other. Okay. So if you imagine this, well, so this would be the landscape you have. And essentially, if you imagine to run an algorithm here with probability, since the number of these local minima is exponentially larger than the number of the true minima, then you get, with probability 1, you get trapped. And if you run a Monte Carlo algorithm, this is what happens. This is for a small system. You find a plateau, and if you increase the size of the system, this plateau goes to infinity. It means that you are never able to learn anything with this object, okay? Now, a single neuron, it's a bit, so this is the simplest possible neuron, and it's already impossible to do any learning. It's kind of scary as a situation, right? So we have to understand what's going on here. And, you know, some years ago, it turned out that, and actually people really believed that this was the case. So you can find papers from the 90s in which people were trying to use genetic algorithms, Markov chain, simulated annealing, all possible algorithms to train this kind of network, and they all observe this exponential behavior of the running time for finding a solution, which means that it's practically impossible. A few years ago, about 10 years ago, I mean, various people were able to find some different type of algorithm which were actually quite effective in finding solutions. So now there's a kind of paradox. How is it possible to find a solution in such a rugged landscape? This is a fantastic computational problem. If you're able to find an isolated solution, like in a golf course, you know, it's a fantastic object, no? So the reality is that, at least from the computation point of view, is not so fantastic, but from the machine learning point of view is interesting, is the following, is that numerical experiments showed that the kind of solution that was possible to find were actually not isolated. So somehow all the analysis that was done, which focused on the dominant contribution, so the vast majority of solution, and when I say majority, I mean exponentially dominating, is of this type. But somehow there are rare events, there are rare regions in the space of solution, which are totally rare from the point of view of counting, however, that are accessible for algorithms, okay? So this is a kind of a surprising result. And so we did analyze this. How did we do this? We introduced a large deviation statistical measure. Essentially, instead of focusing on trying to minimize the energy, we try to maximize what we call the local entropy. So instead of looking for solutions that minimize just the energy, we look for solutions that are surrounded by a lot of other solutions. So we change the measure, okay? And here there's a lot of complicated stuff going on. So this is a large deviation analysis, and I'm not going to enter into the details, but essentially somehow we are shifting our attention onto rare events in this very complicated geometrical landscape, okay? And then by studying this large deviation object, we can try to answer the question, can we find regions that are so dense and that are accessible as the numerics seems to suggest, okay? And the idea is the following. So what is the meaning of the local entropy? Let's assume for a moment that you have this is your landscape. You want to find the minimum in this object here. It's pretty difficult if you know nothing. If you start from a random initial condition, it's kind of tricky. Now, how does the local entropy of this energy function look like? So how does this object here essentially look like? Okay? So this is a true calculation. And so if you allow for large distance, you see that, the definition of the local entropy depends on the distance. So you want to count how many solutions you have within a certain distance from where you are, okay? And so given this surface, if you have a large distance, the local entropy looks like this. And so if you start by minimizing this object, you will end up somewhere here, which is not the optimal solution yet, because the optimal solution would be here. This would be the densest cluster, but it's close to that. And so you reduce then your distance, and you see that you move a little bit towards the optimal solution, and you reduce further the distance, and you end up exactly in the cluster. So you see that by this technique, all this horrible surface has disappeared. All the local minima have disappeared, and you have a very effective method to find optimal solutions, okay? Now, if you do this analysis for the binary neuron, and you can do it also for multi-layer network, at least 2 layers analytically, what you find is that it is totally true that the vast majority of solutions are point-like, but it's also true that there exists a region in this hypercube which is dense in solution. And when I mean dense, I mean the following. Look at this curve. This is the distance, and this is the entropy, so the log of the number of solutions within a certain distance. Now, you see there's a gray line here, okay? And this is the binomial coefficient. I mean, okay, which is the largest number of solutions you could have given a certain position in the hypercube is just the binomial coefficient, right? The log of the binomial coefficient here. And you see that if you store an extensive number of patterns with this network, so if you already have memorized a lot of patterns, this region still, for short distance, has a density which is very close to the binomial coefficient, which means that it's true that you have all these scattered points, but somewhere you have a region which is not only connected, but it's extremely dense, extremely dense, okay? And this is true up to a certain point, which is close to the critical capacity that was computed by Mark, where this cluster disappears. And so as a proof of principle, what we can do is just to take this local entropy and run a Monte Carlo algorithm with an objective function which is not the energy or the cost as you would do normally, but use as objective function this local entropy, right? We can do this by computing in an approximate way this entropy, but I don't have time to enter into the details. And this is what you find. So if you run just a standard Monte Carlo, you get trapped. And if you run the other Monte Carlo with this local entropy, just jump into these dense regions. Now, I don't have time to enter into the details. I mean, there's a paper where, but starting from this new objective function, you can define a huge class of new algorithms which have this objective function as a target. And if you look at them, you will, and compare them to the existing algorithms that are working in deep network, they actually do very much the same, tend to do the same things. Now, the difference is that here we have a principled way of deriving the algorithms and maybe also to improve them, okay? So let me conclude by mentioning a few things. So we call these states the accessible subdominant states. They are subdominant because they're rare, but they are accessible for very simple algorithms, And this is at the base of learning in these very complex networks. And this is related to a branch of physics, of applied math, of probability, which is all the problem of studying out of equilibrium stochastic process. And this is a beautiful field which has a lot of open problems. And by using this measure, you can define new classes of algorithms. You can show that actually few bits of precision are enough to have very efficient neural networks. You don't need to have 32 bits of precision in this deep network to have them function properly. You can have actually probably 1 or 2 bits, okay? That would be enough. And many other things. Now, if I had to bet what's going to happen in the future is that certainly there will be a lot of progress in understanding and improving algorithms and applying these things and so on. But I expect that there will be a huge acceleration once we will be able to build chips that learn on chip. So instead of having, in this network, what happens is that you have a computer that computes the weights with a learning program, and then you transfer these weights on the network and you use the network. The idea is, given that the learning algorithm can be so simple, I mean, I didn't have time to describe that, but believe me, they are very, very simple. You can actually think to build a device that performs learning on chip. And this is going to, give an increase. I'm not talking about quantum computation. I'm talking about real stuff. And so I think this will provide huge performance, and it's very difficult to predict what's going to happen, but for sure something extremely interesting is going to happen at that point. Okay.